In our discussion on electromagnetic waves, we essentially said that electromagnetic waves consist of regions of alternating electric fields and alternating magnetic fields as described by the following diagram. So this is one particular example of a single electromagnetic wave that is propagating in the positive direction along the x-axis. So this is our x-axis, this is our y-axis, and this is our z-axis, which is coming out of the board. So notice the green region is our electric field, which is alternating along the y-axis. The blue region is the magnetic field, which is alternating along the z-axis, and the direction of the movement of our electromagnetic wave is in the positive direction along the x-axis. So the direction of the electric field is perpendicular to both the direction of the magnetic field and the direction of the motion of our propagating wave. Now, in our discussion on electromagnetic waves, we also said the following. So we said that the speed of electromagnetic waves inside empty space is equal to the constant c, which is equal to E divided by B, where E is our electric field and B is the magnetic field at any given moment in time. And we also said that this is equal to 1 divided by the square root of epsilon naught multiplied by mu naught, and this value is equal to 3 times 10 to the 8 meters per second. Now, where exactly does this relation come from, and how can we get the following value? So, let us now prove this equation to be true and that the speed of electromagnetic waves is in fact given by this value. So we're going to derive electromagnetic waves from Maxwell's equations. So, let's begin by assuming the following two important assumptions. These two assumptions will allow us to derive our equation as well as this value, the speed of electromagnetic waves. So, let's begin by examining assumption number 1. Let's consider an electromagnetic wave that is traveling in a region of space where there is no electric charge. So if there is no electric charge, the Q value is 0. And if there is no electric charge, that implies there is no electric current. So if we take Maxwell's equations of electromagnetism and we apply the following assumption, our equations become as follows. So equation 1 tells us that the closed integral of the dot product of E and dA is equal to 0. Equation 2 tells us the closed integral of the dot product of the magnetic field and dA is equal to 0. Equation 3 tells us that the closed integral of E and dl is equal to negative of the derivative of the magnetic flux with respect to time. And finally, equation 4 tells us that the closed integral of the dot product of our magnetic field B and our displacement dl is equal to the product mu naught epsilon naught and our derivative of our electric flux with respect to time. So, these equations are known as Maxwell's equations of electromagnetism, and we were able to use this assumption to make this equation equal to 0, this equation equal to 0, and simplify the final equation. So, this is assumption number 1. Let's examine assumption number 2. Let's assume we are dealing with a sinusoidal electromagnetic wave that is traveling in the positive direction along the x-axis as described in the following diagram. Now, in the previous lecture, we essentially discussed the mathematical representation of an electromagnetic wave. So we said that any sinusoidal wave is given by the following equation. So y of x comma t, where y is our vertical displacement along the vertical axis, is equal to a, the amplitude multiplied by sine of kx minus omega t, where k is equal to 2 pi divided by lambda, and omega is known as the angular frequency. It's equal to 2 pi multiplied by frequency, and the velocity of our wave is equal to omega divided by k, which is equal to lambda multiplied by frequency. Now, if you're unfamiliar with these equations and this equation, go back to the previous lecture in which I discussed the mathematical way to represent electromagnetic waves. So using this equation, we can essentially represent our electric field curve and our magnetic field curve in the following way. So the electric field, or the magnitude of our electric field, that depends on the x value and the t value, is equal to the amplitude, the peak electric field E naught multiplied by sine of this quantity, and likewise the magnetic field, which varies along the z-axis. So Bx comma t is equal to B naught, the peak or maximum magnetic field of sine kx minus omega t. So these two equations will become important in just a moment. So now let's begin our derivation. So we made our two assumptions. Now we're ready to apply our derivation. So we want to apply Maxwell's third equation. So this equation, given by this formula, is also known as Faraday's Law of Electromagnetic Induction. So let's begin by only looking at this section of our electric field within our electromagnetic wave as depicted in the following diagram. So we have the y-axis, the x-axis, we have the electric field, which has the sine curve. So let's consider a small rectangle with a height given by change in y and a width, an infinitely small width, given by dx. So this distance is change in y, this distance is dx. And let's apply equation 3. So let's begin by looking at only the left side of equation 3. So we want to ask ourselves, what exactly is the value of the closed integral of the dot product of our electric field and our infinitely small distance given by dl? So let's begin by examining the top and the bottom section of our rectangle. So if we examine along the top and bottom sections of the rectangle, we see that our quantity, the dot product of our electric field at these points and our infinitely small distance dl is equal to 0, because the angle between our displacement dl and the electric field at these 2 points is 90 degrees. So because cosine of 90 is 0, that implies that this dot product along the top and bottom sections of the rectangle is also 0. So now we are left with the vertical sections of our rectangle. So if we examine the vertical sides, we obtain the following result. So notice we're moving counterclockwise along the following rectangle. So let's suppose we begin here, we move up this way, down, and back to this position. So now we want to ask ourselves, what is the electric field at these two vertical regions? So the closed integral of the dot product of the electric field and our infinitely small distance dl is equal to, so we begin by examining the right side. On the right side, the electric field is given by E plus infinitely small increment given by dE. So notice at this position, we're assuming the electric field is given by E. but in this position, we're assuming our electric field is given by E plus dE. So at this position, the electric field is E plus dE multiplied by change in Y, because our change in Y is our height, minus, because here at point we're going up and here we're going down, minus our electric field at this point is simply E, and we're multiplying by change in Y. So if we multiply this out and we subtract, we get the following result. So dE multiplied by change in Y, this gives us the left side of Faraday's law, the left side of the following third equation. Now let's call this entire equation, let's call this I. Now let's move on to the right side of Maxwell's third equation, also known as Faraday's law. So what exactly is negative of the derivative of our magnetic flux with respect to time? Now, by definition, magnetic flux is equal to the product of our magnetic field B and our area A. Now, notice our area A of the following rectangle remains constant. So this is a constant. We can bring it outside of our derivative as shown. So this is equal to negative of the derivative of the magnetic field with respect to time multiplied by A. Now, area A of the rectangle is change in Y multiplied by dx. So this is equal to dx multiplied by change in Y multiplied by negative of the derivative of our magnetic field with respect to time. So let's call this equation equation I. So now, because these are equal and we know the left and right side, we equate equation I to equation 2I. So I is equal to 2I, and that implies dE, change in Y, is equal to negative dB dt multiplied by dx multiplied by delta Y. So, delta y's up here on both sides, we can cross them out, and then let's bring dx to this side. So we see dE with respect to dx is equal to negative dB dt. Now, actually, both the electric fields and the magnetic fields, as seen from these two equations, depend on both the x value as well as our t value. So that means we have to take the partial derivative. So this is equal to the partial derivative of the electric field with respect to x, where x is allowed to vary while t is constant, and this is equal to the negative of the partial derivative of the b with respect to t, where t is allowed to vary while the x is assumed to be constant. So let's label this relation as relation A. So this will become important in just a moment to prove the following relationship. So we see that in this section, we essentially applied Maxwell's third equation, and we applied it to the electric field. Now, let's take Maxwell's fourth equation and apply it to the magnetic field. So because we're assuming the charge is zero, there is no charge in the area where our wave is propagating, Maxwell's fourth equation becomes as follows. We have the closed integral around some closed pathway is equal to the dot product of the magnetic field B, and our infinitely small displacement dl is equal to the following quantity. So let's begin by outlining a rectangular closed pathway as we did in this case. So we begin at point 1, move to point 2, then to point 3, and back to point 4, and finally back to point 1. So this is our closed rectangular pathway along which we're evaluating the dot product of the magnetic field and our infinitely small distance dl. So we begin by evaluating, by calculating the left side of Maxwell's fourth equation in the same way that we calculated the left side of Maxwell's third equation in this case. So the closed integral of the dot product of the magnetic field B in our infinitely small distance dl is equal to. So let's begin at position 1 and move to position 2. So when we're moving from position 1 to position 2, our displacement vector and the magnetic field vector point in the same exact direction. And let's assume that the magnetic field at this point is given by B. So this is equal to B dot product change in Z, where change in Z is the height of our rectangle, which lies along the Z axis. Next, we're going from position 2 to position 3. Now, when we go from position 2 to position 3, the angle between our magnetic field at that point and our displacement is always 90 degrees. So that implies the dot product of these two quantities from 2 to 3 will be 0. Next, we move from point 3 to point 4. Now, the displacement, the direction of our displacement and the magnetic field point in the opposite direction. And that means we have a negative sign. And let's assume that the magnetic field at this position, an infinitely small distance dx to the right, is B plus dB. So we have B plus dB dot change in Z. And finally, when we go from 4 to 1, that is once again 0 because the angle between our magnetic field and our displacement is 90. So these cancel out. We can actually evaluate this and we get the following result. So we distribute, we subtract, and we get the following. So the left side of Maxwell's fourth equation, our closed integral of B dot product dl is equal to negative of dB multiplied by change in Z. So now let's solve the right side of our equation. So the right side is mu naught multiplied by epsilon naught multiplied by the rate of change of our electric flux with respect to time is equal to, well, these are constants, they stay the same, and by definition our electric flux is equal to the electric field multiplied by the area, and the area of this rectangle is constant, so we can take that out, and the area is change in Z multiplied by dx. So the height multiplied by the width of our rectangle. And that's exactly what we get. So this is equal to this. So we know what the left side is. We know what the right side is. Let's actually equate them. So this quantity is equal to this quantity as shown in the following diagram. So notice that we have change in Z appearing on both sides. We can cross them out, and if we rearrange our equation, we get the following result. So once again, we're dealing with partial derivatives because the magnetic field and electric field depend not only on the time, but also on our position x along the x-axis. So we have the partial derivative of our magnetic field with respect to x, while t is constant, is equal to negative multiplied by mu naught multiplied by epsilon naught multiplied by the partial derivative of the electric field with respect to time when the x is constant. Let's label this equation equation B. And finally, we are ready to prove our initial statement. So let's begin by taking A and taking the derivative of this function. So we know what E is. E was defined earlier. So if we take the partial derivative of E with respect to x, that is equal to the negative of the partial derivative of the B with respect to t. Now we know E is equal to E naught multiplied by sine of kx minus omega times t, and B is equal to B naught multiplied by sine of kx minus omega times t. So if we actually take the partial derivative of this with respect to x, we get the following result. So k, E naught sine kx minus omega t. And if we take the partial derivative of this with respect to t, we see that the negative will disappear, and this is equal to omega b naught sine of kx minus omega times t. So this sine term appears on both sides. We can cancel them out. So we see that k multiplied by E naught is equal to omega multiplied by B naught. So now we solve for omega divided by k by bringing k to this side and b naught to the other side. We get the following. Now, by definition, omega divided by k is simply equal to the velocity. So the velocity is equal to E naught divided by B naught. Now, because the electric field and the magnetic field are always in phase, that means we can replace the peak electric field and the peak magnetic field with simply the electric field E and the magnetic field B at any given moment in time, and this is equal to the velocity V. So this basically tells us that our electromagnetic wave is composed of oscillating electric fields and oscillating magnetic fields. So if we know the electric and magnetic field at any given moment in time, we can use this equation to solve for the velocity. Now let's take relationship B and let's follow the same exact procedure. So now we want to take the partial derivative of B with respect to x instead of t, and we want to take the partial derivative of E with respect to t. So we basically take the partial derivative of B with respect to x, we equate that to negative mu naught multiplied by epsilon naught multiplied by the partial derivative of E with respect to t. And this is exactly what we get. So B naught divided by x naught is equal to mu naught multiplied by epsilon naught multiplied by omega divided by k. Now omega divided by k is simply the velocity, so we replace this ratio with simply V. So B naught divided by x naught is equal to mu naught times epsilon naught times V. So now we take this and solve for the velocity, and we see that the velocity is equal to 1 divided by the square root of the product of epsilon naught and mu naught. So we know these two values are constants. So we have 8.85 times 10 to the negative 12 multiplied by 4 pi times 10 to the negative 7. We take the product, take the square root or raise it to the power of 1/2, and then we take 1 divided by our value, and we get 3.0 times 10 to the 8 meters per second. So this is the speed of our propagating electromagnetic wave. It's the speed of light. So we were able to show that not only do electromagnetic waves consist of electric field and magnetic field, electromagnetic waves move with the same exact velocity in empty space given by these two equations, which is equal to 3 times 10 to the 8 meters per second.